It's washed. And
What?
3, 2.
All right, guys. Welcome to the first white paper circle of the semester. As you guys know, I'm Sid, presenting. This is Ruthin from high school, actually. Yeah. The memes get progressively worse. Just as a heads up. Yeah. So today I'm gonna present about DAG BFT consensus. And this is the agenda, quote unquote, for today. I start off with just like a basic overview of what consensus is. And then the bulk of the presentation is really just understanding how DAG BFT works. And then there's a couple more recent developments like Narwhal and Tusk and Bullshark that we'll cover in not so great detail. And then quick section for plug for Andrew, who was a BAB alum, who did work with this at Paradigm. So just a little plug, and then question section at the end. So with that, we'll go ahead and get started. So Byzantine fault tolerance is basically just how equipped is a system to handle bad actors and machine failures. So the question it tries to answer is how many participants do we need for a given amount of bad actors to agree on a set of actions? And long story short, with this long drawn out proof, we see that we need the number of participants needs to be greater than or equal to the number of 3 times the bad actors plus 1. So kind of just like this diagram, what it's trying to just show is if we had this castle, which is just like what we consider like our sequence of actions, how many of these people who are trying to protect this castle can flake or just be bad actors, and we can still protect this castle. This is kind of just an analogy that's often used to describe this problem. And then this meme. So one way we could go about this is proof of work. So proof of work basically has miners prove that they executed transactions by guessing a nonce. And the nonce is predetermined. So what miners are really searching for is a hash preimage. So kind of jumping down to this diagram down here. Popular hashes have a property of obfuscating the input to an output, and the goal is the nonce is the output, and what miners are trying to guess is what is the input. And the difficulty of this hash is adjusted by changing the number of zeros in the nonce. So the fewer zeros there are, there's less digits for you to guess, so it becomes easier for miners. So another property of hashes is that they're random. So there's no deterministic way to determine what a hash preimage is. Otherwise, the hash is considered broken in the first place. So it's basically just miners do a lot of work to just guess numbers. So a few benefits of this is provable security. Based off just the hash function that you have, you can guarantee that no one can game the system by deterministically knowing what the nonce is beforehand. You can adjust network difficulty, like I said, with the leading zeros, and it's neutral compared to proof of stake, where you need no starting amount of tokens to start mining. Some of the cons of this are high energy consumption, which is very popular with the merge. You spend a lot of energy just guessing random numbers. And there's a higher barrier of entry because you need a lot of specialized hardware to be able to guess these nonces quickly compared to large mining rigs. So it's really, a lot of people end up like pooling resources together and pooling money together to have a profitable mining rig or like setup. Another popular consensus mechanism is proof of stake, where validators are randomly selected to create blocks and confirm which blocks they made and which ones are correct. So to guarantee good behavior, validators have to stake amount of tokens to prevent bad activity. And block finality, which is a concept we'll cover in a little bit, is achieved at certain checkpoints where you need 2/3 of validators to basically commit and say, okay, up until this point, we know that these blocks are valid. So just as a side note, this opens up an attack vector where bad actors only need 1/3 of stake to prevent finality. So someone could basically just, I don't know, buy 1/3 of ETH like all the ETH circulating and try to say, okay, I'm going to prevent consensus from reaching finality. There's a few ways to go and prevent these methods that we won't really cover, but that's just an example. Some other examples of bad activity are double signing blocks, which is basically where validators commit or sign off on 2 blocks for a given round. And this poses a big network security threat because you don't know which block is real for a given validator. And if a validator double signs, they get slashed and usually they get kicked out of the network and they can't validate blocks. Another bad example of bad activity is validator downtime. Let's just say your node just stops working. You have like a power outage or something. So you can get slashed for that. Doesn't necessarily mean that you get kicked out of the network, but just another example. So some pros of this are you have less energy consumption. You're not guessing a bunch of random stuff. There's lower barriers of entry in terms of the hardware that you need to get started. You don't need an insane like mining rig. You don't need to spend tens of thousands of dollars on just like the ASICs that you need to guess these hashes. It's improved decentralization in that sense as well, since more people can have stake and set up hardware to contribute to these validators. And less tokens need to be issued to incentivize network activity. Some downsides of this are, though, that you have no provable security. So, and this kind of bounced off the second idea that it relies on the inherent value of the token that you're staking instead of computational power. So let's just say the value of ETH just like crashes to like, I don't know, like $2. Technically, some bad actors say, okay, I can just buy a lot more of ETH. Like it's a lot easier to buy 1/3 of the circulating ETH and try to prevent consensus from happening. So there's no provable security in that sense. So that's just 2 very popular consensus mechanisms. And I guess something that we haven't really covered yet is how do we actually reach consensus? And this varies a lot from chain to chain, from ETH to Avalanche to Cosmos. But the general idea is that someone sends transactions to mempools, and miners or validators, we could just call them nodes in this case, perform state checks and execute transactions. This is actually something that varies very much from based on which chain you're using. And then after doing these state checks and executing transactions, the nodes gossip commits and votes around the network to reach quorum, which basically says we have a certain amount of people participating on these set of transactions and attesting that they're correct. And then once quorum is reached, the block is broadcasted to the whole network. And like we talked about earlier, how do we know when information is set in stone? So that relies on the idea of finality. So finality is basically just a notion of when a transaction is a part of a block and that block can't change. So there's a few different flavors of this. One of the most popular one is Ethereum, which has probabilistic finality, which basically says over time, it becomes less and less likely for your block to be reordered or not included in the chain. This is part of like a trade-off in terms of I guess liveness and security, but this is very popular as we see through Ethereum. There's also an idea of absolute finality, where once a block is included and added to the chain, it's final. Like you can't move it around. And Tendermint, which is the choice of consensus for Cosmos chains, needs at least 2/3 of validators to pre-vote or pre-commit to a transaction for it to be finalized. And if 2/3 of validators want to like change the order, then they're gonna have to submit a change and say, okay, we want to reorder the blocks, and then 2/3 of validators on the network get slashed and get kicked out of consensus, which is very unlikely to happen. So it's absolute in that sense. And if okay, and then the last one, it kind of relates to both of the previous ones, which is economic finality, which is the idea that reordering blocks or not including transactions in blocks and not being final has severe economic penalty, which is kind of what we see with absolute finality for Tendermint and also probabilistic finality for ETH. It becomes a lot more expensive to move these blocks around or move these transactions around just economically as time goes on for ETH or just in general for Tendermint. So this is another incentive mechanism to prevent people from just changing blocks around and having finality.
Question was, what is the difference in reorders between can you also explain reorgs too? Like, what is the difference in reorgs between proof of work Ethereum and proof of stake Ethereum? So pre-merge and post-merge, are you looking at 51% like how it was in proof of work? Like, is that the same? Does that same notion apply for proof of stake Ethereum as well to reorg? Like, what are the different conditions? How did they change?
I'm honestly not sure for proof of stake. I know for proof of work it's just 51% of the network, which is basically like a fork. Like you basically have to fork the chain. And then depends on which fork has more people mining on it for proof of work. But I'm not sure for proof of stake with like the whole difference between block proposers and block miners and all that stuff.
Like, I think for proof of stake, the way that it works that so you have kind of have like original like slots of block, right? Like a subset of validators go on like each block of the slot, but then everyone has to go at the end of the epoch. The thing that happens now like is that overall epoch vote fails, right? Because like if the overall block vote fails, it's like make a new block. And but the overall epoch vote fails, they can throw out the epoch, right?
Okay. Yeah. That also kind of relates to like the attack vector I described earlier, with like the 1/3 stake to prevent finality. I think if they don't reach consensus in like 3 or 4 epochs, then they just like run consensus all over again because they just think like there's I think it's part of Casper, which is
So,
yeah.
not really. So after like epoch is voted on, it's kind of like right? And then
Yeah.
no, once the next epoch is voted on, that epoch is considered finalized. You never get to change. You're right.
Okay.
So when we talk about like a reorg within a slot, are we referring like is that existent? Is that a thing, or is it just not reaching consensus? Like, can you still reorg within a slot within those things? Say for example, like someone is pre-assigned a slot like 1, and then someone else is at slot 5. There's no way for the block validated slot 5 to be before slot 1 whenever the epoch is finalized.
No way.
So then reorgs don't exist in this. Reorgs in the way they exist before don't exist within the
Yeah.
system.
Like, you're just like failed to come to consensus on the people slash.
All right. Are there any questions with regards to just consensus overall?
Yeah, wait, Tim, can you explain like the first thing you said about 32 epochs and like how they have to do the next one? Okay.
Yeah, so basically, so you to like each so you have each block is assigned like 1 out of 32 slots in epoch, right? So like for example, each block is around like 12 seconds, right?
Yeah.
Epoch is like 15 minutes, right? And then basically you as a validator are assigned to 1 block in or 1 slot in each epoch.
Okay.
So that's why we kind of like have to like split it up. And if you haven't split it up, that gives people more time to make a block.
What do you mean split it up? Split what up?
So like each validator does not like vote on each individual block, right? Like as a validator, you're selected 1 slot.
Oh, by split it up, you mean like the slot assignment?
Yeah. So like
Yeah.
you have this big pool of validators, and each validator gets like assigned like 1 slot,
Yeah,
right?
yeah.
And then you do your slot vote, right? And then after the slots are done, everyone comes together to vote for the entire epoch,
Yes.
right? And if the epoch passes, and it's considered confirmed,
Yeah.
right? And once the next epoch passes, the epoch that was confirmed becomes finalized, and the new epoch becomes confirmed.
What do you mean by slot voting? So you talk about epoch voting, like that makes sense. What is the
So
like, what
it's
is
slot
slot
voting, like so let's say that like you have like this like 1 slot, and there's like 1 out of 30 or 1/32 of the validators in this like pool that's supposed to go to the slot, right? So like amongst this pool, right, 1 validator is selected to make the block, right? And the other validators will vote on that individual block. So there's a bunch of slots in 1 epoch.
But it,
Yeah,
you
so
still
within
need
each
to
block.
come to consensus on every single slot. But then this
Yeah, so each
confirmation only
subset of
happens.
validators comes to consensus on what the block is for that slot.
What is the subset of, so, 1/32
Yeah.
of the validators
Yeah.
will come to, like, they only need to validate one of the slots. Got it.
Yeah, which is like
I mean, essentially, the cause of the it's because you don't need PDFT. You don't need to come to consensus every 5 seconds. Like as Tim saying, you only need to come to consensus on the 1 slot that you have. So like you have, if say you're running just one, so like every single validator in Ethereum is just 32 weeks, right? You take 32 weeks to run a validator. You have these big organizations like Coinbase that'll have a bunch of quote unquote validators, but they're considered one validator, right? Like, so they run a bunch of these like 32 week validators, but actually they have like set 30,000, so 30,000 validators. So some portion of those validators will go to every single slot within the block, right? And so they just need to validate that one slot with that one validator. So if you're only running one 32 week validator, then you only need to validate one block in 6.5 minutes. And in 6.5 minutes, one slot. So your latency time goes from I need to validate every 5 seconds, like on osmosis, to I need to validate something every 6.5 minutes. Yes.
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 I mean, everyone does come together to validate like all the blocks again, but again,
It's-
you're still only doing that.
So it's just two operations.
Can you explain like the reorg like analogy again? So like if you
So-
don't agree on the entire epoch, then what happens? You
So
have to
basically, like,
restart?
kind of like what happened, like the Berkey org that was like kind of like one chain, right? And all of a sudden, there's like another chain that happens to be longer
Yeah,
that comes out of nowhere.
Really?
So the reason that I guess like it doesn't really happen too is because like as a validator, you're assigned like a specific slot number, right? And like you can't change that slot number. So if you make a block that's supposed to go like slot 5, it naturally go like slot 1 because there's another block that's supposed to go into 1. And if you go to come to consensus, just like have to like try like make the block
So
again.
like in the case, although it's unlikely, if it did happen, then like all the validators would get slashed and all of the blocks in that particular epoch would be considered invalid and they would just have to start over with like the same, like the transactions that were in those blocks would be considered just like unverified, like sitting in the mempool again. And they would
Even,
have to
like,
restart
if like the epoch
if
fails.
the epoch fails.
I think so, yeah, they're just throw everything out. So.
Interesting. And all the validators with each of the slots get slashed.
Not really. I mean like you only
Who gets slashed?
Slashing only happens on double sign. So like, for example,
Yeah, but
if
like
I'm
Tim was
just
thinking about slashing the reorg.
there's
Trying to understand what you're saying.
slashing of the reorg. I
I think if like somebody like they voted like actually quiet like
Yeah.
Yeah,
Yeah.
I'm curious about that.
Cool.
Yeah.
All
Sorry.
right. So now we talk about the good stuff. DAG BFT consensus. So I guess kind of just like before I start this off, Tim kind of briefly touched on this, but the way we traditionally view a blockchain is just like, I'm gonna say it's like a linked list, right? We have like you have hashes pointing to the previous like block in our chain, and we have like the state root, the Merkle root, all that fun stuff. And the idea behind DAG BFT consensus is, excuse me, kind of abstracts the whole idea of a chain away. And we kind of just look at bundles of transactions and we leave it up to the actual application to determine what that chain looks like. So I'll just start off with that. So our original question was, how do we guarantee some properties of a distributed system with n participants with f faults? And DAG BFT consensus separates the consensus logic from the network communication, and it has the application layer interpret the state machine data. So basically, all the validators are doing are just confirming which blocks to add to this chain in a specific ordering. They don't actually execute the transactions or anything. They just focus on ordering and validating the transactions. So another note is blocks aren't really a thing with DAG BFT consensus. It's really just bundles of transactions. So the way it works is we have a bunch of validators across several rounds. So in our directed acyclic graph, each validator has a bunch of transactions that it bundles together and it proposes it to all the other validators in a given round. And in order for a vertex to proceed from round 1 to round 2, it needs to have edges back to at least n minus f validators from the previous round. So if I have, I guess we don't really consider round 1 in this case, but for round 2, for this block right here from validator 1 in round 2 to be valid, it needs to reference at least n minus f messages from the previous round. F is the number of faulty nodes in the system. And we won't really cover why it's n minus f, but it's basically to just guarantee, it goes back to the idea that you need n is greater than or equal to 3f plus 1 honest participants in your network, or participants in your network to guarantee correctness.
I think you can explain that here. I think that's important. Like if you need 3f plus 1 honest participants and
You need 3f plus 1 participants. Yes.
then f here represents what percentage of the 3f plus 1? 1/3, right?
Yeah.
So
Okay.
like 1/3 faulty like
Mhm.
validators in the system will break the system.
Yeah.
Just like what you see with Tendermint.
And we see this idea continue to round 3 and round 4. So this is just kind of building up like a basic framework of, we have bundles of transactions and we have separate rounds. And why does it matter why we have rounds? So like I said, you reference n minus f vertexes from the previous round. So each validator replies with a signature if it hasn't responded to the valid. Okay, a validator responds with a signature if it hasn't responded to the same validator already for this round, and the data has persisted. So this creates the idea of a certificate. So we can consider this to have like a certificate. Like this edge existing means that this validator has signed off on this block from this round. So since we need n minus f people to attest on blocks from previous rounds, it's basically saying, okay, I looked at this transaction, I validated it, and I think it's valid. We need n minus f validators to say that to move on to the next round.
Yeah, that makes sense. So like, what is the certificate?
What is certificate?
What is the certificate launch? Like, how is the certificate used?
We'll get there. We'll get there.
Let's
And-
see.
And then validators move on to the next round if they have these n minus f vertices with valid certificates. So this kind of introduced, okay, this is kind of the cool part, quote unquote. So if we have two validators that have the same vertex from a given round locally, then they have the same vertex globally.
Okay, wait. Vertex again, it's just like there's like a transaction.
It's a bundle of transactions.
There's like a transaction that both of them, like, can you like point out when you say like a vertex, it's like they are like drawing the same transaction from like one previous validator. Can you just like point to it when you say like?
So, okay, so we can consider this to be like, let's say this is like, each validator has their own local graph that they're looking at.
Yes.
And basically what the idea is that if two validators with their completely like they have no idea what the other person's like graph looks like.
Yeah.
But if they know that in one round that they both have the same vertex.
What do you mean same vertex?
So like if they have this vertex in both graphs.
They can't both have the same vertex. That, what you're pointing to is only for validator 2. So I'm trying to understand what you mean by both vertex, same vertex. Do you mean the same intersection of?
They're both building this graph locally.
In the graph here is what?
The graph here is just like the bundle of transaction from different rounds.
Because like when you say shared vertex, the reason it doesn't make sense is because validator 2 is like there, so like no other validator can have that same vertex because they're not validator 2. So I'm just trying to.
This is
understand
no,
what
but
you
they
mean by
send
shared vertex.
they send this out to every other
So
validator.
you're saying every single validator has all 4 validators' data.
They broadcast the message.
Okay, so everyone's
Yeah,
okay.
everyone has that. So then the idea is, since we have the certificates, like n minus 5 people from each round, say that, okay, I think this block or this bundle from this validator in this round is valid. You can basically reach this idea that if 2 validators had the same bundle in a given round, that they're the same vertex, just like globally. Because basically what happens is, if we look back at this graph, since they share the same edges going back to previous rounds, and so we know that these blocks are valid, since it's the same certificates and the same round, that they all reference the same information. so that they're both referencing the same ground truth, even if they're both, even if they don't share the same local view.
So just to confirm, you're saying like, say there's 4 validators in our scheme,
Uh-huh.
every single validator, like their local state is keeping track of all 4 validators'
Mhm.
information at each round
Mhm.
based on like the communication.
Yeah, based off the messages they
whatever,
broadcast.
broadcast.
Yeah.
Okay, that makes
I have a really dumb question. Why we did multiple rounds here?
That comes in handy when we're actually committing the information. So like right now we're just like agreeing on stuff like from like one person's viewpoint, but then we actually, when we come to like putting it all together, the rounds idea comes in handy because you basically end up electing a leader for a round, and that leader commits their block. So they say, okay, my block gets sent out to everybody, and then what happens is if they're the leader, they look back at the transactions they reference and they check if the previous blocks were committed or not. If they were, then you don't do anything. If they weren't, then they say, okay, since I have all the certificates for this round, I know that these ones are true, and that those blocks in that round reference true blocks that have already been committed, that these blocks are also valid.
I was gonna ask, why is it like big block?
It's really not.
But they're not necessarily
Yeah.
correlated. That's so like the issue being that like because we have the idea of rounds don't necessarily correlate to when blocks are proposed.
Yeah.
And the whole idea behind this is that you don't have any guarantees that those are transmitted to all validators. Like basically, like you're just trying to admit as many people as possible. I committed this block. Take it my block. But you don't have any guarantees on everyone receiving. It's like the 2 generals problem, right? Like I can send to you my block, but you can send to me that you got my block. But the issue is then I have to send it back to you that I received your block at some time. Then it's just like turns into it's like recursive loop where like neither of us have any guarantee of at what exact time we received the message of the previous message. So like it's basically like 2 general problems things, but basically communication networks are hard. This is a mechanism to make it easier to come to consensus on the same thing.
When it says like if 2 validators have the same vertex, so like is it just completely random, or
What do you mean by random?
like what determines if they have the same vertex? Like
What determines the same vertex is if they have the same edges pointing back to blocks or bundles from previous rounds.
Is every bundle correlated with like a certain like does it have like the round as a like, part of its data?
Yeah.
Like
so it's a guarantee that every single bundle of transactions is going to end up with multiple validators.
Yes, you need to have n-f people agreed saying like, okay, this is true, for you to be able to reach that conclusion. Yeah.
otherwise the network.
Yes.
Yeah. Did you have a question? Okay.
So what ensures that 2 like validators will have the same like kind of they're building their source of truth off the same way?
That's where the edges come in, because you know that you're referencing the same like ground truth. Like you know that the edges that you're pointing back to are true blocks that everyone else agreed on.
I'm sending you a bundle with like the timestamp here is the round.
Yeah.
So if I send you a bundle with round 13 is absolute across the whole system.
Yeah.
So then once like n-f validators have come to consensus on the bundle, say from like if you go back to this graph, you go back to the like say for example it's like around 0 and around -1 and around -2. This is very valuable because once all these 4 validators come to consensus on say the block that validator 3 proposed in round -2, you now can clear all the history behind round -2. Because we know you guys all have the same common history, and because you have the same common history around -2, that means your common history must be the same for every round behind round -2.
Yeah.
Does that make sense? So
Yeah, so the main idea is that with this property, you're basically able to say that given this block in a current round, I can say that all of that block's history is the same across these 2 validators, because they end up referencing the same information over and over again. So this also like the idea of like recursively referencing the same information over and over again. And this also implies that bad agents can't lie because they can't prove that they have the n-f edges pointing back to the same set of transactions. And I guess the more math approach to this is kind of with this diagram here. So if I have 3 validators propose 1 block here, which is block 1, and I have 3
What is that?
n is the number of participants. 3 validators propose, let's n minus f. We have n is 4, f is 1. So you have 3 people propose 1 block.
But I thought, and my,
Yeah, like these are the people that you reference.
oh, but like, don't all of that. Lose, and like one of them- Unless it's just like off. Like you off by-
They're proposing a malicious history.
Yeah.
like, That's what they're doing.
Yeah.
that's what- I guess it could all be like off.
Yeah, so you have 3 people, like let's say you have block 1, which references these 3 people, 3 validators from your
Yeah.
round, and you have block 2, which references another 3. And if you take the intersection of these 2 like sets of edges, you see that P1 and P2 are common. And you know that at least one of them is honest, since you only have 1 faulty node. And since you know that P1 is common through both, you can say that the edges from P1 are valid, and you can reference those ones.
Is it not n equals 4 because there's 4 people?
Yeah, you have 4 participants, but block 1 references 3 people, block 2 references 3 people. But since they both have different, like you have P1, P2, P3, and the second one is P1, P2, P4. So they're not exactly the same set of what do you call it?
So how big did I do one?
Well, it doesn't matter because you just know that one of these 2 is faulty. So
is this assuming that P1 and P2 share the same person?
Why is it not two guaranteed honest?
it could be either of the 2. You know that at least one of these 2 is honest.
No, I mean, why is F one not?
Why is F equals?
Why does F equal
Oh, this is just like an example.
one?
You could, but then in that case, you break the condition that n is greater than or equal to 3f plus 1. Because n is 4 in this case, f is 1, so n is greater than or equal to, yeah. So in this case, you know that these 2 blocks are the same, so that you know that one of these 2 is faulty. So you can just reference the information from one of these 2 and use that to build your history back.
This
This
is
is-
breaks about it.
Yeah, and
That's like
that's the fundamental
core
assumption.
tenet of BFT is that like, if you can't make the assumption, then the communication protocol breaks.
Yeah.
So like, for example, like if in proof of work, more than 51% of people are malicious, it's broken, right?
Yeah.
Is it really malicious? You know,
Yeah.
that's what the people actually want, so yeah.
So then this is kind of something that touched on briefly as well. So we might have all these like wonderful transactions here and there, but the question is, going back to the idea of like a blockchain, how do we recreate that idea of state? So any thoughts from anybody as to how we might go about this? It's not related to the rounds, but it's related to the data structure that we're using, which is a DAG. I'm gonna put you on the spot, Rutland.
You want to give a hint? Sid?
I did. It's related to the inherent data structure that we're using. Well, you can't because it's an acyclic graph, right? Oh, go for it.
It's just like how to use DAG, so how many users are in one place. How many of them?
It's not about the confirmations, but we're trying to go through the transaction that we have and turn them into a linear chain. I'll put it that way. Yeah, it's top sort. You could topologically sort the DAG since you have a bunch of vertices with edges pointing backwards, and any valid topological sort ensures that you have a valid and accurate state machine for that. And 170. And 170. But yeah, you could basically, once you have a vertex, you could basically go back through its history and sort the edges that it references and just recursively go back and based off the transactions, you can just start building history and start executing. And by the time you get to a certain V, you can have the entire state machine's data. Yeah. Well, I think that answers one of your questions. Yeah.
Asking for a friend, can you tell me what topological sorting?
It's a way to turn a graph into like a linear ordering. So like if you should I just
I think
yeah.
You have to come before me.
I'll pull up the visualization for it.
If it's all connected, grab the end and like put it up.
Yeah.
That's what
It's like turning this thing into a linear.
maybe you should explain what.
Yeah. So basically, I guess looking off this diagram, if we have this like giant like mess and we want to figure out what this like state of the current machine is, if we want to like get to that idea of like a linked chain, basically what we do is this is kind of in reverse order. You could like reverse the edges and go back, but we have this being our current V that we just looked at. And then let's say V references a bunch of nodes going back here. And then these nodes end up referencing a bunch of other stuff back here. That's basically the idea that we're going back to. And at each state, we just, since we have like this linear order, now we can go from 0, have like a state machine. Then we update that with the transactions from 6 and 1, 5, 4, and so on. Any other questions so far?
Where does the n minus f come into play here? Like, does it come into play with the top sort of the graph?
Well, you know that the vertex that you're referencing, like the first vertex you start from, references n minus f other vertices.
In order for a vertex to be included in the top sort, it needs to have n minus f valid.
Yeah. And it kind of just goes back from there. So
N minus f.
you basically have n minus f edges coming out of one node, pointing back. It points back to n minus f unique vertices, and then those vertices also point back from the previous round.
So you have like the top of graph
This
one has n minus f.
pointing back. Yeah. Yeah. Yeah.
Wait, can you go back one slide?
Oh yeah, I guess I didn't finish through this. So validators don't actually care about what the transactions they're validating contains. Like it could have like invalid information. Like you could turn like account like 0x01 to have like negative balance. They don't care. That's up to the state, or that's up to the application to look at and execute and be like, okay, we don't execute this transaction. We just ignore it since it's invalid. I think you should ask Rob that. He's MEV boy, big MEV guy.
What is like in what context are you looking at the system? Like reordering. The thing is, this is completely this is what it's referencing. It does not matter what they're transmitting. It's all before the consensus. Like consensus is completely independent of MEV right now too. Like the validator and POS is already chosen. No, reordering is something that is like very tied to POW.
Yeah.
Good reward. Transaction reordering is very different than block reordering.
Yeah.
You can do transaction reordering. Transaction reordering works in any system that allows you to have like validators have some control over what blocks go in, or alternatively, some entity has some control over the ordering of transactions. This is completely abstracted from ordering transactions. We're specifically looking here on the ordering of bundles.
What about like it seems like there's, I guess you could choose, you have to be creating a sort of district.
Yes, because like this is like I think Tendermint does a really good job of this, but basically like the mempool and everything here is completely abstracted away from how you come to consensus on the blocks and the bundles. Because all this is asking for here is let's limit the amount of data that any given validator has to store at a given time.
And like which like which parts of like, I mean, you say like it's the word, Ethereum, like which parts of it cannot be done?
Block reorder.
Any other questions? All right, cool.
Or reordering, sorry, not reorder, block reorder.
So now we jump into Narwhal and Tusk, which are kind of building off this idea of consensus or DAG based consensus, with a few additional ideas. So when it comes to consensus, there are two flavors of that as well. So there's synchronous consensus, which has a guarantee that all nodes will have the same information for a given round or a given time, in some allotted time slot. So let's say I start my round right now, and I say that within 5 minutes, all nodes in my system will have the same information. It provides a guarantee, and assumptions for nodes not falling behind. Asynchronous consensus, on the other hand, does not have that requirement that nodes need to have the same information in some given time frame, which is technically a lot more realistic for like real life conditions. Yeah. And
In BFT, not
Yeah,
BFT.
wonderful meme here for reference. So like this is the idea, like in synchronous consensus, you like have this idea like your messages are all going to arrive in a given time frame, right? But let's say hypothetically some node falls behind, then you're kind of just screwed. Like it just breaks that assumption, and a node would have to catch up in some way, but then they don't have a valid history because they don't submit their transaction in that given time period, blah blah blah. So it just causes a lot of problems.
So if you're getting all your information, this consensus node, but that node doesn't have the same information as another node, is your data just outdated or false data?
Your data isn't necessarily, your data can be outdated. If it's included in that round and it has valid edges to like other information from like a previous round, then it is considered valid. But like your node might end up falling behind, which is why asynchronous consensus isn't necessarily preferred, because it just has no guarantees for like it has no real bounds. Like it could take forever for some information to get broadcasted to every other node in the system. So it's just rather unsafe set of assumptions, which is something we cover down the line with something called partial synchrony. But yeah. So Narwhal and Tusk are two protocols that build off this idea. So Narwhal is a mempool protocol that distributes transactions under asynchrony assumptions. So it focuses just on data availability and the certificates that we talked about earlier. And it also has this really interesting property called garbage collection. So let's say that going back to our DAG here, let's say we're at round 4 and we know that we have edges to everything between round 2 and 3. So if we know that we have references to round 2 completely, we know that the information in round 2 encompasses everything in round 1 and everything in round 0 and everything round -1 and so on and so forth. So garbage collection basically says, well, if I have this information up to a certain round and we know we've covered everything in previous rounds, we can kind of just garbage collect all the old information since we know it's already encompassed.
up to that particular round.
Yeah.
All of the validators would make something.
Yeah, they need to store it because it's already been committed to the overall state machine's state.
So like, there is a minimum number of like, as a function of R, what is the minimum number of like the topological sort?
The minimum length of the topological sort.
Yeah.
Ours is a round number. The minimum length of a topological sort. It could just go back one round. Like there's a minimum bound of going back one round, but I guess there's no real upper bound unless your transactions have already been garbage collected. Like you just keep going as far back as you can until you hit like a wall. Like all other transactions that a certain set of blocks reference have already been committed. Wait, say that one more time.
I thought you want to minimize the number of rounds left to go back to.
Not necessarily.
It's not like better.
Storing less state, yes, but one thing that ends up like when you're actually committing blocks, like I mentioned, I'm not sure if I cover this later, but I could like write up a quick example. Basically, like in even number rounds, there's a leader that's like randomly selected, and their block gets committed to the state. So they basically say, okay, my block's being committed. Let's look back at its causal history and keep recursing back until we find all the blocks that haven't been committed already, and let's just commit them all at once. So what ends up happening is that everything else in that round, like from all the other validators, just ends up not being committed. But what we have is this guarantee that down the line, at some given point, all these blocks will be covered and won't be garbage collected. So you end up covering all the information. What the benefit of going back through all these previous rounds is you have increased throughput because you're looking back at more transactions overall. You're not just committing one block at a time, you're committing that block and that block's histories, blocks, and so on. Runtimes in terms of like throughput or latency. In terms of latency, I'm not sure how it compares to proof of work, but in terms of throughput, you have a lot higher throughput because you end up going through a lot more information in a given like commitment like round, like where you like commit everything to one state. Because like what ends up happening is like in proof of work, for example, you have one block that everyone's just racing to find the nonce for and commit. But with this setup, you're not competing to find a given nonce. You're just trying to make sure people validate your block, and then eventually, when you get to an even number block round, you know that someone's going to commit their information, and it's probably going to contain your blocks from previous rounds. So it's less of a race and more just about going back through all the previous things that we've committed that we are guaranteed to be correct since they reference n minus f edges, and just committing that information at once. It's less of a race.
And this is committing locally?
Committing is global. Like the leader part is global. There's no like real constraint of you wanting to go back like a certain like you don't really care about how far back you want to go. Like I guess okay, to answer your question, yes, you would want to go far. You would want to keep it as shallow of a search, but that's not something we really optimize for. Like it's not something that they
It's
optimize
not
for.
something we optimize for, but it's like you.
You would want to keep it shallow. Yeah, it would be better. Yeah,
It's a byproduct.
yeah.
Like it's like it comes as like a complementary part of the system.
Yeah. Like the
You're optimizing for throughput plates,
yeah.
but then like it happens to be that like state can get reduced in terms of like what values have to store in a given
Yeah.
time block.
Like the more validators you end up happening, the more rounds you have to go back because there's only one validator in every even number round that commits their state. So you end up having to kind of just go back a little bit deeper each time because during each round, like if I have like 50 validators, only one person's gonna get their blocks committed for a given round. So like you have a guarantee that eventually down the line everything's gonna be committed, but the more validators you have, the deeper your search is going to be, which is where garbage collection is useful because you can garbage collect all the blocks that you know have already been committed and you know are part of valid state.
Is garbage collecting local or global?
It's global. Wait, I messed up. It's local. It's local.
Okay.
Yeah. So it reduces like the constraints for validators locally.
You have like validators that choose to do garbage collection and some that choose to make different types.
You totally could. It doesn't really make a difference. Yeah. Yeah.
So
Yeah.
into garbage collection, would it just be a matter of like storage, or would it also be like it would be unnecessarily parsing the source of data, or would it stop because it's included the necessary time?
It would stop because it ends up seeing a block that's already been committed, like when you're recursing back.
Okay, so it's just a matter of storage.
Yeah.
But all these things are encoded in like a client that like validators just run. So
Yeah.
like all these details for the most part are just like pretty much abstracted away from like most consensus algorithms are pretty abstract array validators. Unless they really want to get very wonky with like MEV and other systems, then.
Do you have to manually garbage collect or can it happen on?
It can happen. Yeah.
Like if you run a client that garbage collects, no garbage.
Yeah.
collect for you.
You could set up, you could tweak your own parameters for whatever validator to like garbage collect after like 5 rounds or 10 rounds, whatever.
Someone has to keep all the points.
That's more, I think that's more of a state machine thing to maintain, or like application level thing to maintain.
It's possible for like every validator to like garbage and then change them off because they have to say.
This is different assumptions than what you see like in Ethereum and in like POW initially, where
Yeah.
like you need to necessarily store every single block on a full node or a validator because you could technically reorg 1 million blocks, right? And like hard fork all the way back if you got to do the network to Oh no, proof of work.
They have stuff. It's like they're even considering doing state requirements, but like they right now they need to make that somebody. Not everyone needs to do it, but somebody.
I think this is
Yeah.
second order.
Yeah.
One issue.
Yeah, I think it's a level of abstraction away. Okay, and then Tusk is, oh, I messed that up. That's supposed to say synchronous. Tusk is a consensus protocol that focuses on ordering transactions with low overhead, and it's synchronous, not asynchronous, so it provides a termination guarantee. And this is kind of, we're just gonna black box this, but it turns the DAG that we have from Narwhal, which is our mempool protocol, into ordered blocks with no extra communication. With the magic happening in the sense that since you know that the blocks have valid edges, you don't need to actually send any other information out. You can just locally say, okay, since we reference valid information, we just commit that. Yeah. Yeah.
Oh.
So this is like the blocks and certificates that you were, I think, were asking about earlier. But yeah, so this is where we're covering like leaders and certificates. So if I'm at round R, the blocks that I propose, or the blocks that I propose must reference n-f certificates from previous rounds. And then based off this, if once I have those n-f certificates, I can generate a new certificate for my block with the signatures of these validators and say, hey, my block is now possibly valid, or it's valid based off these commitment globally. It happens at even number rounds. No, a specific leader is elected and they say, okay, my block is valid. So let's go through my block's causal history and commit everything in its causal history. Biased in what's
they choose the history that is associated with their
sure, but you need the n-f like attestations from other people, from other validators from previous rounds, and those need yeah.
I mean, I guess it's like
Yeah. So once I have those certificates, I can say, okay, I can just move on to the next round. Like I can just say, okay, now I can start proposing another block because, hey, n-f people said that my block from this round was valid. So let me just start proposing more blocks. And that continues for all the other validators, and you just end up building this DAG structure. And going to the idea of commitment. So let's just say like round 3, I decide to commit my my block. So what I end up doing is I look at this block for this validator and I look at, okay, what do the edges point back to? And if those blocks have not already been committed, then I can say, okay, I can order this topologically and linearize those set of blocks and commit that. And this process continues over and over again. And we eventually have the idea that all this information will be committed at some point. Any,
That's not.
yeah, it's randomized. Mhm.
Well, so like they have like different transactions.
Yeah, yeah.
So like what if like multiple validators like pull up the same transaction? And, like,
Pull up the same transaction, put it in different blocks.
yeah, like the transactions all symmetrical, right?
Uh-huh.
Just like pick out like one. What if like different blocks have the same transaction?
That's valid. It's up to the application layer to decide how to execute it then.
And there's the idea of this like whole thing that you just have parallel. Like,
Yeah, basically, because everyone's doing work in a round. It's just the idea of when does that work get committed globally. Yeah. Any other questions? Cool. Now we tackle Bullshark.
So like, since it works, certificates are generated on, like, your certificates are generated, but it's still not committed.
Yeah.
And then afterwards, can you explain how certificates go into that diagram?
Well, basically, for you to have a block in this round, it just checks their certificates to make sure you have n minus f people on that certificate.
Would only check the certificate,
Yeah, it makes sure the certificate has
and
Ref-
it's like.
yeah, like say digital signature. Yeah.
Is every block eventually validated by every single
I wouldn't know. It's not validated by every validator because you only need n minus f people to look at it.
Is there like a specific order in which that happens based on the line?
A specific order that what happens?
That like for example, for the one on top left, then it gets moved to the bottom.
Wait,
Like-
which one?
Like how does?
Okay.
I'm trying to avoid my question. So like, is there an order in which, okay, so like if I validated in this round, somebody else validates the same block in the next round? Like, or is it completely random?
Like, do you
No.
know who the the proposer, the leader is at every single odd number round?
Do you know who the leader is at? It's randomized.
But I'm saying, like, when I look back here,
When you
find
look,
the leader at r minus 2, and I'm at r equals 3, I'm the validator here. Do I know who the leader is at r equals 1? Like, why do I go back through that to the cosmic history to know that's the leader?
yeah. I think you would know because it's broadcasted to everybody on the network. So yeah, everybody would know who the leader is at a given round.
Because also, in order for them to receive that message, they would have to have gotten a message from the leader saying that they are the leader for that round. Does that make sense?
The leader,
As in, like,
the
the
leader
leader,
is just the person right before, right?
the leader is the person who proposed it, the on number round. So here, the leader 2, this would be validator 2 is proposing your 1 equals 3. And then there's leader 1 supposing 9 equals 1. And when leader 1 says, I'm committing, they also, I'm assuming that that's the note that they're the leader at that round.
Any other questions? All right, cool. So now we tackle Bullshark, which introduces the idea of partial synchrony, which is a mix of asynchrony and synchrony. So the problem with Tusk that I kind of touched on is that it doesn't guarantee liveness. Liveness is the idea that everybody is up to speed with what the network is currently doing. So with Tusk, if let's say some validators were just like super cracked, they had like great access to like network, like great like fiber optic cables or something, or they just had like really good hardware, they could just speed through validation and a lot of nodes could fall behind. So that kind of puts people at a disadvantage if they just don't have good hardware, or some messages just never get sent or received. And Bullshark solves this with partial synchrony. So the idea behind partial synchrony is you have let's just say like this timestamp. Let's call it just like X. So before that timestamp, you can guarantee that all information has been committed. Like you could be as asynchronous as you want, but as soon as you hit timestamp X, all information will be like up to speed for all validators.
So what happens, like, how does that solve the all behind problem? Like, what if you're still behind?
There's a few like tricks where you could have like weak edges in the graph to like kind of just like jump ahead and be like, okay, I'm just gonna skip forward to this block that's already been validated, and then I'm gonna keep going on from there and start referencing like other edges. That's
So it's still possible. But it would feel like
yeah. So, and then after that timestamp X, you once again have periods of asynchrony where you're like, we don't know exactly what's happening, but at some point, like let's call it like X+1, we're gonna get like checkpoint again and say, okay, we're gonna make sure everything's committed. So that's the main idea behind Bullshark. And through this, there's some magic that happens where it achieves consensus in just 2 rounds, which is what Darius talking about, how many rounds you have to look back in just 2 rounds instead of 3. And like I mentioned, it achieves this fairness through weak links in the graph. It's a tad complicated to like draw because there's like a few different ways to implement it, but that's just the general idea behind it. Any other questions?
There's some examples. I'm just thinking on one optimal, just say a best protocol or blockchain.
So in terms of consensus, Bullshark is kind of like considered state of the art right now in terms of like this kind of DAG based consensus. Narwhal is considered the best like mempool protocol at this point when it comes to this. And I guess examples of this are Diem, which is a blockchain by Facebook. I guess I think Aptos uses it too.
Aptos uses odd stuff.
Which is also DAG BFT, which is a
It's
flavor
a
of this.
iteration of this. There's this whole meme with blockchains and L1s in general that like the new shiny thing is a new consensus algorithm. So this is the new shiny thing
Yeah.
right now. But like if you talk to the Avalanche people, they will tell you ours is revolutionary. If you talk to Algorand, theirs is revolutionary. Like everyone wants to find the best consensus algorithm. So I think there'll be more
But then
iteration on
people
this.
don't necessarily be like building on whatever the best.
Yeah.
Like
Yeah.
you find that like a lot of the ecosystems have like instant usage of the chains, despite having a really interesting white paper and like a very revolutionary model. Because it's just like that.
Yeah.
Like network effects compound quickly. Very hard to move apps off of something once it's already been created. So
And then this is kind of further reading if you guys are interested on a high level. It'd be like that. It'd be like that. So this is kind of further reading Cosmos Out Tendermint. It's a proof of concept by people at Paradigm. Shout out Andrew Kirilov, which swaps out Tendermint consensus for Narwhal and Bullshark. And they basically just kind of explore how to actually implement that, how to potentially run like EVM compatible like logic on it, I believe. And it's just like an interesting experiment to look at. I guess we could like just scroll through it. I guess kind of just like background. Cosmos. Let's see. Yeah, so Cosmos is, I guess, how would you describe Cosmos?
Cosmos is the framework for building a modular blockchain stack. Like if you're looking to spin up a new blockchain, using like a PBFT consensus, like Tendermint consensus, the Cosmos SDK is a really good framework for doing that. Cosmos in general is considered to be like a whole amalgamation of things of like Tendermint, IBC, Cosmos SDK,
Mhm.
but
Yeah. So
also
Cosmos,
was made here. Like Cosmos was made in this office 5 years ago. So like this is the Tendermint core office that we're in right now. So
Yeah.
yes.
yeah. So Cosmos, like Ruthan explained, is kind of just like a set of tools for you to like spin up your own chain. And with this, you can choose like the application layer, you can choose the consensus mechanism, and just like a whole lot of other like interesting things. And what the folks at Paradigm did is they said, okay, since we can swap out consensus, what would happen if we use Narwhal and Bullshark for consensus and mempool instead of Tendermint? So they kind of just dived right into like the Cosmos SDK. There's this idea of the application logic and the consensus layer, and there's an interface between the two and clients. And their goal was, okay, instead of using Tendermint core here, what would it look like if we were to implement it with Narwhal and Bullshark? So that's eventually what they dive into here with their whatever like tech stack, I guess. And they just ran a few experiments with it. And yeah, this was I think this was a hackathon project that they just had internally, but it's a really cool just like proof of concept at just exploring how these kind of things work. So if you guys want to read up more on this, I'd definitely recommend kind of just trying to understand Cosmos and ABCI, and then looking at this and seeing what they did. And I guess you could dive into their I think they have like a GitHub repo in here somewhere, but
Summary, like, why is it better to?
yeah. So the goal behind Narwhal and Bullshark is to achieve high throughput with low latency, which is the entire spiel of DAC BFT. The idea of achieving high throughput with low latency.
And consensus in general.
Yes. Yeah. In the frame, yeah, that's a pretty important point actually. Yeah, I think that's about it. Any other questions? Fine.
TBD.
TBD.
Very excited.
After Adam 2.0 by Ruthan himself.
Someone. Yes.
Ruthan himself.
Yeah, I think Sid wants another person.
Yeah.
Can we get a hint for Sid?
Oh, it's not a very good bar for what like the sort of GFE from ground up.
Thank you.
Can you pull up the DAG? This one, by the way?
The what?
Of this, the paradigm.
Which one?
Paper? Above this, not this one. What's that one? A little bit higher. Does everyone kind of understand what this looks like and how this works? Of like how, okay. What are the questions, like shoot out questions, like what are the questions of this? Like, just in general, like what is this diagram showing? Can I give it a try?
Sure. So, like I said, the idea behind Tendermint is to separate consensus from application logic at a very primitive level. So, what this diagram is trying to explain is how to organize your mempool, which is shown right here with Narwhal, from your consensus engine, which is Bullshark, and how do you connect that information into this ABCI interface. ABCI interface basically describes how you interpret your transactions that have been confirmed into state logic for your application. So the question is, okay, I have these transactions, cool, in a mempool, that's fine. I have this consensus engine, cool. How do I turn this into something that applications actually use under this framework of ABCI, which is application blockchain interface? So what they did is they basically built out kind of just like their own like software to kind of interact with the mempool and create this flow of, you have a client that submits a transaction, I believe that goes here. This routes it into your mempool, and Bullshark, the consensus engine, references this mempool and sends it back to your middleware, I used to call it. And this middleware interprets it in a way that's compatible with ABCI to send it to your application logic. That's my attempt at this.
Let me find the link to
Tendermint, like,
Tendermint like diagram that I was.
oh yeah.
Basically,
In the browser.
Arc.
You gotta use Arc. Yeah.
I don't-
What is Tendermint?
In here.
Yeah, it's yes.
That's-
I think Rutland is pretty good at explaining this one actually.
Okay, so basically, like the goal of the cosmos SDK in general is just to like a really big trend recently in blockchain systems has been how do we decouple these different parts of what makes a blockchain so that we can optimize every single part for specific applications, specific blockchains, etc. So different blockchains, different distributed systems want to take different trade-offs with the applications they want to enable. So Tendermint is the core consensus engine for the Cosmos SDK. And this is a diagram of how exactly Tendermint and the application blockchain interface with the Cosmos SDK. So application logic is where you're writing your dApps, like contracts and everything. The goal of this is that you want to be able to segment this into like the life cycle of a transaction. So what you're going to have is that whenever transactions get broadcast into the mempool, say for example, you want to submit a transaction. So what you're going to do is you have a wallet in your browser, so Kepler. Kepler then is going to send a that has an RPC endpoint. So what you're going to do is you're going to broadcast your transaction to that RPC endpoint. Kepler is running what you want to call a full node, right? What a full node does is it's trying to service queries, transactions, and submit them to the mempool, which then will be validated by validators and put into blocks. So you submit it using your wallet to sign the transaction, to confirm the transaction, it broadcasts it to the full node broadcasts it to the mempool. Then inside the mempool, what you want to check is you will only want to have transactions that are valid, the ones that are included inside a box. You don't want to include invalid transactions, wouldn't make much sense. So you're gonna have very basic checks on the transactions themselves. This is check TX. So like in the Cosmos SDK, you can include these like checks on specific kinds of function calls to see if the transaction is valid. Very easy, like out of bounds checks, not super complex integration checks. So for example, a really easy check is just confirming, okay, like, is this like a valid person to call this contract? Is this, if this specific function within this contract is permission, say for example, only the creator of the contract can call that function, you'd want to check that in check TX. However, something more complex needs to be determined at the point of transaction execution. Say for example, like a slippage tolerance on a DEX trade would not be picked up by check TX because you have no idea when you submit the mempool if that transaction is valid. So transactions can still fail, but you don't want them to be invalid. Does that make sense? So in the first step, you're going to be sending your transaction through the node into the mempool. Then after that, what's going to happen is the proposer for the block has been pre-selected by the consensus algorithm. So they're going to reap the transactions from the mempool, which will then send the proposed transactions to the mempool to the proposer. In Tendermint right now, it's like first come, first serve. So like whenever you submit your transaction, it's just grabbing the transactions that are served. In Ethereum, pre-flashbots, this used to be done with like a priority gas auction. So like depending on which transactions were the most highly valued, that's how they would be ordered. And like flashbots does something similar right now. But like you can just assume that like it's just grabbing the transactions that will have the possibility of being included inside the block. Then you have your consensus logic. So this is the tenant part. So we've done every single step, right? We've done the checking on the transaction, we've done the broadcast to the mempool, the proposer already has the transactions, only then does consensus happen. It only happens when the new block is processed through consensus. So the idea behind this is that we want to take all those different steps, which are integral parts of the transaction lifecycle, be able to break them up into different parts so we can optimize every single part. So this is a really good diagram explaining like at a high level how you can break up the transaction lifecycle from submitting a transaction, inclusion in a mempool, to broadcasting it to the proposer, sending it through the consensus logic, to then the consensus logic being broadcast with all these different things that will then service it back to the state machine that will then update, say like with the DAX trade, it'll update the reserves of the DAX. So, and that'll all be done through this application block interface, breaking up your transaction mempool ordering and consensus from your data availability and state machine. So this is your execution. Actually, I'm not sure where DA falls in here. It falls in the right side.
I think it falls on the mempool.
Yeah,
I think it falls on the mempool side.
but I'm querying here, right? Like when I'm querying the state, I'm querying here. So I'd assume that the data
Oh.
would fall on the side of the
Application.
execution. Like you have so you have your consensus and transaction ordering, and then you have like your what is the current state of the state machine, and then what possible functions can I run in the application. So that's the, I don't know if that makes sense, but that's very good. Yeah. So then if we go back to the previous example for the paradigm paper, you have your consensus and transaction ordering, your Bullshark, your consensus, Narwhal, your transaction mental ordering, interacting with through the ABCI, your application logic, here being the EVM, the state machine, as well as the data availability of the state machine. So again, you submit transaction, goes through the transaction mental ordering, checks it against the application logic, broadcasts it back, goes through consensus, then broadcasts updates that application logic. Sounds good.
All right. Thanks everyone for coming over and attending this white paper circle, and more to come soon. That's what I'll end off with. Thanks everyone.